Hello, everybody, and welcome to Model Talk. The goal of this lecture is to give you an overview of really what the point of statistics is, and in general, what we are going to be trying to do with each of the statistical analyses we are going to be utilizing this semester. So, this starts with a really basic question, which is what is the goal of statistics? Well, really, what we are here to do is to explain data. And for us, these data are going to be primarily in the form of numbers. Now, we use statistics really only in cases where we are unsure about our data. We don't try to estimate the number of feet people have or the number of moons around the Earth, right? We don't need statistics for that. We really only use statistics for things that are uncertain. This is actually part of the criticism people have of statistics, is that we get things wrong sometimes. Well, the only reason we get it wrong is because we don't use it for things that we are sure of. So really, what we are interested in are differences between people, or differences even within a person, depending on what the statistics you're doing. We're really only going to be using statistics when there are differences. So we like things that have some kind of uncertainty or variance. So usually when someone is doing statistics, they'll try to come up with some kind of model. They'll model the data, just like people making model airplanes. They're trying to make kind of replicas of the larger airplane. Well, for us, what we try to do is we try to model the data. We try to figure out how to either predict the data or come up with some statistical model that will allow us to take what is going on in what we've seen so far in a group of people, and then try to predict it later or to understand it, why it's occurring. The first model that we are going to be looking at this semester is the mean. So the mean will be the first model of the data we use. So what is the mean? Well, really, it's a measure of central tendency, and we're going to get to that in more detail later, but we don't need to worry about that right now. But what we do want to talk about here is how it's a measure of central tendency, but it's more complicated. So let's try to visualize our data. So if we visualize data, let's say we have the number of friends, close friends, 5 people say they have. We have one person said 1, one person said 2, 2 people said 4, and 1 person has said 5. Well, how would you describe the data? Remember, that's what the goal of statistics is. So how would you describe this? Well, to do it succinctly, you might look towards the median or the mode or the mean. In general, we're going to be looking at the mean. So in the case here, we've got the mean. And this score, the average, is the value that is closest to each of the scores combined. So if we wanted to estimate some random person's number of friends, we could take data from some sample of a population, and the mean would actually be the best prediction based on just the number of people that we have alone. So in this case, let's say these are 5 people from our class. Well, based on the data we have, if there was a 6th person and you had to guess the number of friends they have, you might look to the mean and say 3.2 is a pretty good guess for the number of friends they would have, just based on the data we have before. Now, I'll show you what happens to the mean what happens if you don't use the mean in a little while. But for now, we're first going to check our model fit. So for all models, we want to see how well it fits, because we can already tell it's not perfect, right? 3.2 does not describe everyone. There's a lot of difference going on here. There's difference here from 1 to 3.2 and 2 to 3.2, 4 to 3.2. We've overestimated the number of friends for these people, and we've underestimated the number of friends for those people. So, how do we check the fit? Well, one of the things that researchers often do is look from our model and go back to our data, the real data we have, and see the difference between the two. In this case, it's fairly easy. We can take the data we have, and we can take the mean and subtract that, right? We take our scores, subtract the mean, and we can get an estimate for where our mean is in terms of how much total error there is. So in this case, the lines here connecting the means and the points are deviance scores. We're going to talk about that a decent amount this semester. And that's just the difference from the scores to the mean. That's a deviance score, how different it is from the mean. With these negative numbers, that means that the mean has overestimated the number of friends, and here, these have underestimated the number of friends. However, if we just add up all of these deviance scores, it gets us to 0, which obviously isn't true in terms of the total number or total amount of error. But I should note that when you get 0 from deviance scores, that only happens with the mean. If you were to pick other numbers, so let's say 2, you'd have a different deviance score, not 0. So to fix this from our attempt to find out how much error there is in our model, we square our scores. So we take the deviance scores and we square them. And this is equal to the sum of squares. And the sum of squares, or the sum of the squared errors, is a relatively decent measure of the accuracy of our model. But the problem with sum of squares, and why we're not going to just stop there, is that it depends upon the number of scores you have. So for example, for these 5 scores, our sum of squares is 10.8 when we have a mean of 3.2. But if we basically replicate these scores, our sum of squares doubles. Is our mean any worse of a model when we just have the same scores over again? Of course not. It's the same in terms of how well it describes the data. So because of that, we take the sum of squares and divide by n minus 1 to get variance. This is what variance is. It gives you about, on average, how far away your scores are going to be from the mean. It's a general way to think about it. It's also just another term for how much error there is. So variance is the average error between the mean and the observations made. This is also, as I said, a measure of how well the model fit the data. But the problem here is you'll notice that the notation is S or SD squared. S squared. That means the units are squared. So if I were to tell you how many friends on average the variance score is, it would actually be 2.7 friends squared, which obviously doesn't make a whole lot of sense. So to get around that, we take the square root of it. And this gives us standard deviation. So therefore, the sum of squares, variance, and standard deviation, are all measures of fit, of how well the data fit the model. Small standard deviations mean they're close to the mean, larger ones when they're farther apart, depending on the units you are using. This is why we will say that the standard deviation represents how spread out the data are, how far away from the mean they are. Now, I said earlier I'd show you what happens if you use a different score, not the mean. If you used any other random value, in this case 2.5, well, what happens? The incorrect squared error would be 15. The total variance that's incorrect is the total deviance divided by n minus 1. We can get an incorrect standard deviation. Well, what's going to happen? Well, our standard deviation is 1.64. The incorrect standard deviation is 1.94. So any other value you pick other than the mean is going to be worse to predict the data than what the mean is. You're going to get a larger standard deviation calculation for any other number than the mean. And as I point out on here, if you don't believe me, try it out. Pick a couple other numbers, just test it out, and you'll see that this standard deviation estimate is going to be larger for non-mean values. All right, so all of what we're going to be talking about is kind of in what we would refer to as the linear model. And that is where you have some kind of outcome which is equal to your model plus error of some sort. We generally use linear models to describe our data. This is true for correlation, regression, t-test, ANOVA. All of these are variations on the same linear model. You have some kind of model plus error. So while correlation and regression look scarier than the mean, it's still somewhat the same general model. And we know all models have errors. This is why throughout the semester we will be looking for more and more advanced statistics to add more complexity to our data. I mean, the data in the real world is complex. So what we'll be trying to do is kind of address errors that we haven't taken into account previously. So we'll start off trying to say that the mean is the best model. And then we'll add on to it from there and compare the mean to other forms of models. And if the mean is better, we'll stick with it. And if not, we'll move on. Now, another component of this is that different questions require different models. So if you're trying to predict a score on a test, that might require a different model than if you're trying to predict if a drug works better than a placebo, for example. But for what we are going to be doing, we're basically going to be sticking to the linear model realm. And to just show you how much what we've done so far is going to be similar to later in the semester, when we get to correlation and then regression, which is based largely off of correlation, we're going to be looking largely at what we just did, where you have your data plotted, but you could have it in two dimensions. And we're going to take into account not just deviance from one variable to another, but we're going to look at two of them and look at them together and see how well our correlation fits the data, our model of our data, how well that fits. So really, what should you be getting from this? Well, I think it'll be helpful if you watch this, go back and watch the descriptive statistics lecture, and then watch this again to kind of get a fuller understanding of it. But right now, we should know that the mean is the most basic model of the data, meaning it's the most basic description of the data. And that we can use standard deviation, variance, sum of squares to kind of estimate how well the mean fits the data. Because sometimes the mean is not going to fit the data particularly well. So in this case, we see that here we have two different situations where there are 5 measurements and each has a mean of 2.3. Well, what happens here? The standard deviation for the top is 1.65, but 2.58 for the bottom. Therefore, the mean is a worse model for the bottom than the top. We will be looking at this, trying to get an estimate of how well the mean fits our model, other models fit throughout the course of the semester. So if you can understand, mean is a model, most basic model. Standard deviation, variance are ways to estimate how well the model fits the data itself. You're in pretty good shape.